Let's get started. I'll give you a really quick review, and then we'll see some visualization of vectors, scaling vectors, linear combination, stuff like that. Okay. So these are vectors are probably the basic thing that we will discuss most during the first part of the second half of the course. You can think of it, if you can think of it visually, then it will help you when you try to understand some other more complicated concepts. Okay, so vectors, and then so today we mostly look at vectors and vector addition, scaling of vectors, and then the first important concept is called linear combinations. So we look at linear combinations and span. Okay. Today, if you can sort of like think about linear combination and span visually, that would be great. Okay. So let me remark quickly. Okay. Currently, there are many online tools that would help you visualize these concepts. Okay, like GeoGebra, the thing that we use today. But these are the tools, okay, that help you visualize stuff, right? But you should be able to sort of like have a clear mental model of this concept without the tools. Okay, the tools will help you when you start learning, but if you rely on the tools, if you rely entirely on the tools, then it means that you don't really grasp the concept. Okay, so the tools, given a vector, and when we talk about scaling a vector, you should have some after today. Okay, you should have some idea on what it would look like if we have a vector here, and if we scale it, what it would look like. If we have two vectors and we combine it, what it would look like. If we have two vectors, the span of them, what it should look like. Okay, without relying on the tools. In the beginning, if you use tools, it will be faster. Okay, but don't just look at the image that the tools give you. Okay, try to match the image on the tools with the image that you have in your mind. Okay, and try to make sure that you can imagine the visualization themselves. Okay, yourself. Okay, all right. Okay, so quick review. So this will be on the topic that I'm talking about here was on the video clip already, so you can go back and watch it again if I'm going too quick now. Okay. All right. So vectors and matrices are stuff that are called mathematical objects that we learn in linear algebra. Okay. And vectors, you can think of a vector as a list of elements. Okay. And they are ordered. So the zero here and this zero are not the same thing. Okay, it's zero, but this, if you look at a vector, if you want to think about what it means, it might mean something. Okay, say this is the property of a book. Okay, given a book, you represent a book as a vector, and then you say, okay, the first coordinate, okay, will be 1 if it's a Thai book. If it's not in Thai, it will be 0. The second coordinate represents the fact that the book is hardcover or softcover. A hardcover book is like book hang, alright? And the third one is like, it's a documentary. The next one will be like, is it color, stuff like that. So given a book, you can sort of like describe its properties as a vector. Okay, so vectors ประตูล็อกนะครับช่วยเปิดนิดนึงครับมีใครใจดีเฮ้ยเปิดเท่าไหร่ก็ไม่ได้เอาไม่ได้เหรออยู่ในจิตออกมา not locked. It's jammed.
It's stuck.
You should. You can forcefully open it. So, alright.
I don't want to break anything.
Okay. So 2 ways to think about vectors. One is to think of them as some mathematical objects without thinking about the meaning. The second way to look at it is to sort of like imagine that it's represents some object. Okay. Both perspectives give you a meaningful ways to viewing vectors. So we will use them interchangeably. But mathematically, it's just a list of numbers. Okay, it's just a list of numbers. Okay. Okay. Here you can represent anything as a vector, right? Okay, so I'm going really fast. Okay, so now if you have a vector, each element of the vectors, we typically have elements of the vector as real numbers. Okay, so if you have a vector with length 2, like this, like 1, 2, 5 minus 7, push hard. Okay. Here we can each of these are real numbers. Then we say that look at this R square is a set of all tuples with the first element of the tuple is a real and the second is a real. So these are vectors are inside this set R square. Okay. So this is like a plane. Okay. So you when you have a vector with a two-dimensional vector, we can think of them as a point on the plane. Okay. You can view it as like this. So let's take a look. Okay. I have vector v1 here. This is 1, 2. Okay. You can think of you can swap the coordinates. That would be fine. But this is 1. This is 2. You can say. You can edit it, say minus 5 to be that. Okay, let me zoom in a little bit. Okay, so this is our vector. So there are 2 ways to view vectors. One as an arrow like this. When you look at it this way, it sort of gives you the sense that it's the direction. Okay, but you don't have to really put on the arrows here. So a vector is just a point, okay? So you can just say, let's say, okay, so I don't know how to remove a line, but you can think of V1 as a vector like this in arrows, or you can think of it as just a point, okay? In many cases, look at the vector as a point gives you a better view of the situations, but sometimes giving them arrows sort of like might be useful. Okay, so this is one vector. So let me add another vector. Let's say v2 equals 3 minus 2 over there. Okay, so that's v2. Okay, that's v2. Okay, so you have 2 vectors. You can add them. Okay, you can add them up. So what's the result of the addition of these 2 vectors? So when 2 vectors, when you think of 2 vectors as a point, adding them doesn't give you that much meaning, okay? But if you represent them as an arrow, adding them is like you go along these arrows and then you follow the direction of this v2 down, and then you get the result. Okay, so let me add them here. That's the result. Let me so why do we have that? Okay, minus 2. So let's say minus 1. Let's change this to minus 1. So this is the result. Okay. When you add 2 vectors, you add them coordinate wise. Like the first. Okay, so this is minus 3. You add 3, you get minus 2. This is 2. This is minus 1. You add them up, you get 1. So this is the resulting vectors. Okay, you have two vectors, you can add them. Okay, you can also, given a vector, you can scale it. Okay, by doing scalar multiplication. Okay, scalar multiplication is like you take a real number and you multiply all the elements of the vector with that particular value. So let's see vector u. So this is vector u1. So let me give it a different color. So let me remove this one. So let's call it u1. Okay, where is it? Okay, this is u1. So let me give it a color. Let's say it's red. Okay. So I'll multiply u1 with a. Now a is 1.9, so it's go really out of this window now. So let me. Okay. So if I change the value of a, you can see that. Come on, move. Okay. When a is minus, it go backwards. When a is positive, it go like that. Okay. So this is like scaling of vectors. Okay, you do scalar multiplication and then you scale it. Okay. So given one vectors, if you given one vectors, a vector is a dot. Okay, just 1 point. If you look at all, okay, so let me write down. Okay. So you have vector v1, right? And then we have some number a multiplied v1. You have a scaling of v1. Okay? So v1 is a vector. Let's say it's a vector in R squared. Okay. Sometimes I put on the bar on top to mean the vector. Okay. But if you know it's vector, then I usually don't put the bar because it's messy. But today let me put it like that. Okay. So v1 is a vector. You multiply it with a, so it's a scaling of v1. Okay. But if you look at this set, okay, v1 is a point. So let's look at that. v1 is a point. When I multiply v1 with 2, I get this point, right? When I multiply v1 with a half, I get this point. Now let's look at a set a times v1 for a from for every a from real numbers. What do you get? This is a set of vectors. Okay, you have vectors. You multiply it with all the real numbers. You have a set of vectors. What does this set look like? You get all the points here, right? Okay. Okay. Now it form. What does this set look like? Look like a line, a straight line. Okay. So you have a line like this. Okay, not that straight because my handwriting is really bad. So it's a line like this. Okay. So if you have a vectors, you multiply it with some number, you have another point. But if you multiply with all the real numbers, you get a set of points that form a line. Okay. So visually it's like this. I'm taking A and then I just move around, like take all the A's, right? You can see that it's a line. Okay. All right. Now I have another vector v2 and it doesn't look that nice. Let me change it a little bit. So I have vector v2. Let's say it's 2. And then let's say this is 1, like that. Okay. I can also scale vector v2. Okay. So let's add another number v equals 1, and then let's make a slider, and then let's call u2 equal v times v2. Okay. u2. So okay, this is u2. So let's give it another color. Let's make it blue. Okay. So now I can scale this vector u v2, right? What do you get? You get another line, okay? A set of all possible value of scaling of v2, okay? All right, so now let's get to the nice part, okay? Can I add v1 and v2, u1 and u2? I can add u1 and u2. u1 plus u2 here, okay? You can, let me make it green. Okay. So let me make it a little thick so that you can see it. Come on. Okay. All right. So this is the green one here. Okay. So I have. So let's look at the value a and b. Okay. Try to imagine what I'm going to ask you to. Okay. So you have b to be like minus 1.8. So it go backward to this. Okay. I also have a to be minus 1.2, so it go backward to that. Okay. Can you, if you wanna, and you have the resulting vector u here, can you move u to be up there by changing the value of a and b? What is a? A is the scaling of v1, b is scaling of v2. Can you move this vector up here by changing the value of a and b? How can you do that? So what should the value of a and b be? Positive. Like something positive, right? So let's try to do that. Okay. Okay. So let's do u1 first. Chip. Oh. Okay. So you should follow what it look like. Chip. ดูนะฮะว่ามันขยับยังไง Okay. So if it just move around, it would look like this. And at some point, it touched this vector exactly, right? So, okay. Do you see the? So now let's ignore the arrow for a bit. The addition is a point. Okay. So if you change a, the point move, right? So do you see the trace of the point? So let me show you the trace. Show trace. Can you do that? Okay, let's do it again. So do you see where the points are? The point look like a straight line, right? And it go through this. Okay. Now I want a vector to go up, so let me change b a little bit to be positive. Do you see the okay? Okay. Now when you change the value of a, the vector move, right? What's the direction of the movement of the vectors? It moves along v1, right? You can see it's the same trajectory as v1. Now, when we change the value of b, the vector moves along the trajectory of the movement follows the direction of v2. Okay. So now you can see that you can move the vector here. Okay. All right. So let me zoom out a little bit. So let me ask you one more thing. If I want to be, so you can think of v1 and v2 as the direction of some as a direction. Okay. You have some jet engine and you have two engines. One engine can drive you only on this direction, and another engine can drive you on this direction. Okay. The question is, can you reach this point? Can you go there? Yes, right? Can you go here? Like, can you go here? Probably yes, right? Can you go here? Yes, yes, right. Given these two directions, you can go anywhere in R square. Okay, you can go anywhere on the plane, right? So let's actually do something. Okay, if you want to be here, like this one, what should the scaling be? Maybe that's why let's try this one. Okay, so I should add a, right, a little bit like that, and then I should add b a little bit. Oh, here. Okay, so now I'm at this point. Okay, you can sort of like add scale u1 for a bit and scale u2 with the right amount. You can be here. Okay. All right. So this is like just a quick practice. Okay. So all the green arrows. So forget about arrows now. So the arrows point to a point, right? All these points that we move around, these are what we call. What exactly are they? They are the summation of some scaling of v1 plus some scaling of v2. So we take v1, we scale it, we take v2, we scale it, and we add them up, okay? And we get a point, okay? So given two vectors, we can generate a new vectors by, multiply or scale it, scale the first vector, scale the second vector, and add them up, okay? These vectors are what we call linear combinations. Each of the vectors, like this vector is a linear combination of u1 and u2, v1 and v2. Okay. So a linear combination is just the addition of the scale version of the vector you have. Okay. So this is called a linear combination. This is a really important concept. Okay. So a linear combination is a vector. Okay, just one vector. Okay, but given two vectors, you can have lots of linear combinations. You can have like infinitely many linear combinations, and there shows here like all the points around. Okay. All right. Okay. So two vectors, you can add them up. You can scale them. Okay. 3 dimensions. Okay. Before we go to the 3 dimensions, so let me conclude a little bit. So so you can do what you can do from with a vector. You can add them and you can scale them. Okay. You can add them up. You can scale them, and you can scale and then add and then scale and then add, stuff like that. And the resulting of that, the result of these are linear combinations. So by definitions, vector additions, if you have two vectors with the same length, n vectors, length n, you can add them up like that. And you can also, you also have zero vectors. A zero vector is a really pretty crazy vectors that if you add it with any vector, you get the same vector back. If you multiply it with something, you always get zero. So zero vector is like the most important vector that you can have, I think. You can do scalar multiplications. Okay. Given two vectors, maybe more than two. If given m vectors, okay, if you multiply the first vector with alpha 1, this is the Greek numbers. Greek alphabets. Okay. We love Greek because, I don't know, they are old. They have nice yogurt, I think. I don't know, yeah. We use Greek number a lot, but because Greek yogurt is good for your health, maybe you can buy yogurt at Yogoluto downstairs. I don't have any, it's not paid advertisement. Okay. All right. So if you scale the vectors, I need to cut it out from my YouTube as well. Okay. You can multiply the vector with these numbers, and then you add them up. and this is called a linear combination. So a linear combination is just one vectors. You will have a lot of linear combinations. Okay. Now another important concept is called a span. So let me take this. Okay. So a span is a set of all linear combinations. Okay. So a linear combination is a single vector, but if you take all possible linear combinations, you get a span. Okay. So let me show you visually. Okay. So if you have one vectors v1, a span of v1, what does it look like? So v1 is here, right? So a linear combination of v1, if you have just one number, a linear combination of that vector is basically a scale of that vector. You increase the length or decrease the length, right? So like u1 is a linear combination of v1, one possible linear combination of v1. If I change the value of a, okay, u1, each u1 is a linear combination of v1. If you take all u1, that's the span of v1. Okay, if you take u1, you get a span. So what does the span of v1 look like? A line. Okay. Now, let me. You can think of this visually as well. So you have a vectors. So a span of just a vector is just a line following that direction of the vectors. Okay. Now, if I have v2, the span of v2 is going to be another line, right? u2, right? Another line that look like this. Okay. That's another line that look like this. Okay. Now, all the green guys, these are the linear combination of u1 and u2. Okay. And what happens if we take all the linear combination of v1 and v2? What do we get? We get the whole space. Okay. Like I can just move this around. Like you can see, I can go anywhere, right? Basically, but my scaling is only allow me to go like this far. But I can go to all the points in R square, right? Okay, so that's the span of these two vectors. These two vectors is kind of nice because the span sort of like goes everywhere on this plane, right? Okay. Now let me change v2 a little bit. Okay. So suppose this is v1, and let me have v2 to be let's say 2.5 and minus 1. Okay. So let me clear. So now v1 is this, v2 is this. Linear combination. The span of v1 is vector, look like a line like that. The span of v2 is also a line, but they have the same span. Okay, because these two vectors are in parallel. Okay. Okay. So now, if we take any linear combination of v1 and v2, what do we get? We only get vectors on this line. Okay. So these two vectors v1 and v2, they are different vectors, but it's their span is only just a line. Okay, because they are in parallel. They are on the same direction, sort of. Right. Okay, so this is also another kind of vectors, a set of vectors that you see. Okay, so you have vectors that are in parallel, then it's act weirdly. Okay. Okay, so this is in 2 dimensions. Again, if you have a vector, what can you do? You can find you can have a linear combinations of vectors, and you can also have a set of all linear combination that we denote by span. Okay, so let me move to the 3-dimensional case. Okay. Okay, so 3-dimensional. So let me do the same thing. Let's say v1. Yes. This is a vector v1, and let's say I have a v1. Let me make a slider. Say u1. Yeah, okay. Make it red. Okay. No. Okay. So now, again, when your vector is in three-dimensional space, you can scale it, okay? And you can sort of rotate the plane to sort of like see how it looks, okay? Okay. You can think of it, okay, if you have a pen, you can think of a vector in three-dimensional as a pen, and your fingers here, your hand, will be the origin, like this one. Okay. When you scale the vector, it's go like this. And if you have vector v1, if you take the span of v1, what does it look like? You have a line, okay, line 3 dimension. Okay. So let's have another vector v2. Let's say it's okay. So this is my other vector v2. Okay. What does it look like? So let me rotate it a little bit. Okay. Like that. Okay. So let me do the. Okay. So you have can I have one volunteer? Can you be my volunteer? I'll give him a clap of hands. So, alright. So, his head is the origin, and this is the first vector, like this. Okay? And the second vector is this. Alright? If you add them up, what do you get? You get somewhere here. Okay? If you do if you look at the linear combination, just the span of this vector, you get the direction like that. If you look at the span of this vector, go like that. Okay. Now, if you take all linear combinations of these two vectors, that's the span. Okay. This vector v1, this is vector v2. The span of this vector, what does it look like? It go beyond the square, right? It will look like a plane like this, okay? Okay, it will be a plane in 3 dimensions, okay? If I move his hand like this, what does it look like? It's going to be a plane like that. It's going to be another plane, okay? Now, if you do something like this, and then his other hand also on the same parallel line, okay? So what is the span? What does the span look like? You just have a line. Okay. So if they are in parallel, the span will be a line. But if you move his hand a little bit, then you get a plane. Okay. Because you can go outside the line of the first vector. Okay. Now, can I have another volunteer? So I'm gonna let him add another vector. So this is first vector. Can you be another vector? Give me one hand. Just one hand. Okay. So so if I have this vector, okay. So this vector gives this direction, right? It's a span in this direction, that direction. What are the span of these 3 vectors? Can you go anywhere in 3 dimensions? Yes, right? Because like this 2 vector give you a plane, right? And this one gives you like you can move out of this plane, right? So you can go anywhere. But if these vectors just fall into the same plane, can you use three vectors to get anywhere on the three-dimensional space? No. Okay. All right. Thank you. Give them a round of applause. When you go back today, okay. When you go back home today, imagine that you stand here and then all the vectors are your hands. But you can only have two, right? But if you need more, you can use your leg. But it will be a good exercise. Okay. All right. Okay. So now let me do it here. Okay. Let me give another variable b equals 2 and then u2 b times v2. Okay. So I can move this around. So let's make it look like, make it blue. Okay. Now let's add them up. Okay, u1 plus u2. I have this one. Okay, let's make it green. Now I have two vectors and leaf trace. Show trace. Okay. So now I can move around b1, right? Like this. Move a1. But the green vectors, if you look at that, it will form a plane, right? You can see that. Look like a plane. So let me change a little bit. So letเห็นไหมฮะit's look at like a plane, right? Can you combine these two vectors to get out of this plane? No, right? So if you want to get out of this plane, you need some vector outside this plane. Okay? So if I have 5 vectors and all of them are on this plane, their linear combination will always be in this plane. Okay? If I can find some vector outside of this plane, and I take the span of these two vectors with that one, the third vectors, then I can go anywhere in 3 dimensions. Okay? All right. So this is the sort of like the idea of linear combinations and span visually. Okay. So, but before we go to that, so let me prove you something. Okay. Yes. Yeah. Yeah, this is because we are in discrete math. Okay, so let me show you one thing. Okay, so that's we sort of like right now, if you understand what we've been talking about, you can see that the statement that we just said is this one. Okay, so if I have v1, so we have let v1 and v2 be vectors in R to the 3. Okay. And then we have a span, right? If so we have span of v1 and v2. This will form a plane, or maybe it might be a line. Okay, but if we take a vectors, if let v3 be a vector in this span. Okay, so we have 3 vectors. So we have v1, the red one, and we have v2, the blue one, and they form a span, right? So a span will be like a plane like that. Okay. Now, if I take another vector v3, okay, a linear combination of v1, v2, and v3 will always be on this span, on this plane. You cannot get out. Okay. So let me the statement that I want to prove is this. Okay. Then any linear combination of v1, v2, and v3 will be in span of v1 and v2. Okay, so let me prove it to you. Okay, the proof will be pretty straightforward, but it will give you a view of the definition of span and linear combination. Okay. All right. So proof. You might think that second part of the course that there will be no proof. That there will be a lot of proof. But the linear algebra part will have roughly very mild, a very small number of proofs that you see, but we prove. And after probably 5-6 weeks, we will go ahead and learn about number theory. That will be lots of proofs. Okay, so this course will be like really about proofs. Okay. So, but I won't go really fast because this is probably the first time you hear the word proof from me after Ajahn Thana, right? But we will see some of the proofs. Okay. So to prove this statement, we say like any linear combination of this. So let me translate this back to the something that you learned before. So like for all vector W, where W is a linear combination of V1, V2, V3, right? W belongs to span V1, V2. Okay, this is like for all. When you say any linear combination, so it means like taking any vectors where W is linear. Okay, so to prove this, okay, we need to talk about W first, right? So let's say consider any linear combination W of V1, V2, V3. So W is linear combination of V1, V2, V3. Okay, by definition, if W is linear combination of V1, V2, V3, then what can we say about W? So then there exists alpha 1, alpha 2, alpha 3, the real numbers such that alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 equals W. Okay. When you learn from Ajahn Thana, you have your proof will be like numbers, right? Items, numbers. We probably not gonna do that here because it takes a lot of space. But it's the same thing, okay? Like this is the first one, this is the second one. Okay. Like we use definition of linear combination, right? So W is linear combination when it's the summation of some scaling of V1, V2, V3, right? So there should be some scaling factor alpha 1 times V1 and alpha 2 and alpha 3, so that W is this guy. Okay? So let's go slow, okay? Okay, then what do we want to say? We want to say that W belongs to the span of V1, V2, right? What does it mean to be in the span of V1 and V2? What's the definition of span? The span is the, so let's take a look. The span is a set of linear combinations of the vectors. right? So now, if you come back here, what we want. So let me write it in green. So this is my thinking. Okay, this is me thinking. Okay, so I need to say that W is a linear combination of V1 and V2. And then I have headache. Okay. So when we say W belongs to the span of V1 and V2, we say this, right? It's a linear combination of V1 and V2. Okay. So how can we say that W is a linear combination of V1 and V2? So W is like, you see something here, right? This part of W is clearly a linear combination of V1 and V2, right? But we have some extra V3 here, right? So we need to somehow get rid of V3, right? But what do we know about V3? V3 is in the span of V1 and V2, right? So the fact that V3 is in the span of V1 and V2, it means that V3 is what is it? It's a linear combination of V1 and V2, right? Okay, so we can sort of like rewrite V3 in a way that help us. Okay, so let's deal with V3. Okay, so since V3 is a linear combination of V1 and V2, the exists. I have alpha already, right? So let me use beta B1, beta 1 and beta 2, such that V3 equals beta 1 V1 plus beta 2 V2. Okay, so I'm using the fact that V3 is in the span of V1 and V2, right? So it's in the span, so it's a linear combination. So because it's a linear combination, there are some scaling factors, beta 1 and beta 2, that you can scale V1 and V2 and add them up and get V3. Right? Okay, so using these two facts, we can rewrite. We can write W to be alpha 1 V1 plus alpha 2 V2 plus alpha 3, but we know that V3 is beta 1 V1 plus beta 2 V2, right? And I expand a little bit, do some calculation, and then I get V1, alpha 1 V1 plus alpha 2 V2 plus alpha 3 beta 1 V1 plus alpha 3 beta 2 V2. Is it the span of V1 and V2? Is it a linear combination of V1 and V2? Yeah. You can factor V1 out, right? So last step. So let me zoom in a little bit. This is equal to alpha 1 plus beta 3. Oh no, sorry. Alpha 3 beta 1 V1 plus alpha 2 plus alpha 3 V2 beta 2 V2. So we conclude that V3, that means V3 is a linear combination of V1 and V2 as required. Stuff like that. So this is the proof that of this lemma, of this fact. Okay. Maybe it's a little bit small. Okay, so if intuitively, so this is like, if you understand this, you don't need the proof, but we can be really sure that our thinking is gonna be correct, right? So we need to prove stuff. We need to prove it. So the idea that if you have two vectors and if you have another vector as a linear combination of that two vectors, the third vector is always belong to the span of the first two vectors. You cannot get out. Okay, if you made of V1, so when you say a linear combination, you can think of them as a linear combination as you made of, right? When you say V3 is in the span of V1 and V2, it means like you create V3 from V1 and V2, right? So if you are created from V1 and V2, you cannot get out of the set of all things that V1 and V2 create. So that's roughly the meaning behind this. But we can be sure that this is correct because we prove it. Okay? And the proof is like, maybe this is the first time you see the proof in linear algebra, or maybe you've seen it in high school, but it basically rewrites stuff, taking definitions, apply definitions, rewrite stuff so that it fits the definitions. Okay? There's nothing fancy about it. Okay? Just hard work. Okay? All right. Okay. So I hope this gives you a quick review on vectors. So 3 concepts. Okay? 3 concepts today. You can do vector addition, you can do scalar, and you can combine them, right? When you combine some of this, you get a linear combinations. By definition, a linear combination is this, okay? To be a linear combination, you need to know the scaling factors, alpha, and then you multiply each vector with the scaling factors, and then you add them up, you get a linear combination. And you can take all possible linear combinations and then you get a span. Okay, a linear combination is a vector, a span is a set. You have to be really careful. When you say a linear combination is a span, that's incorrect. Okay, I might slip up something like that, but that's not correct. So a linear combination belongs to a span. Okay, it's a member of a span. All right. Okay, so vector addition, scalar multiplications, linear combination, and span. Okay, a few things. Okay, so I hope this gives you a quick review. We talked about this in the video clips already. So if you need more details, you can always come back, go back to the video clips. All right, so let's have a quick break before we do some practice exercise.